Hi there, and thank you for clicking on this video. This video is going to cover polynomial division, okay, which gets its own lesson separate from adding, subtracting, and multiplying. Now, please like and subscribe if you find this video helpful. Drop a comment or ask a question to engage, and check out the practice set for this skill. It is so important. This is definitely not a skill that you can just watch being done out. You need to practice it for yourself and work through the reasoning on your own. Now, before we begin, it is crucial that you understand and have experience with polynomial multiplication on the area model. One of the reasons I advocate for multiplication on the area model as opposed to repeated distribution is because of the way the area model transfers over to division. If you've been doing polynomial multiplication another way, then you won't have the ground level understanding for knowing what we're doing. So if you need a refresher, please check out the video linked up here somewhere. Okay, and you can fast forward through the adding and subtracting and focus on the multiplication part. Make sure you do some practice problems with the multiplication, and then come back and join us here for the lesson on division. Now, to do polynomial division on an area model, we are going to leverage the fact that like terms are on the diagonals when the polynomials are in standard form. And what I mean by that is this. If you have the area model set up, your like terms are going to be organized on those diagonals. So you'll have the upper left with the highest degree, you'll have the lower right with like your constant, and then your like terms are going to be arranged on the diagonals. Okay, so that's important that we remember that. Again, if you don't know what I'm talking about with that, it might be because you haven't done the multiplication on the area model and you really need to go and do that first. All right, so we're going to check out an example with numbers first of all. So suppose you have the problem 30 divided by 5. If I wanted to model that on the area model, it would look something like this. So we would have a rectangle. The area would be 30. And the height would be 5, and we would be looking for the other dimension, okay? So I want you to stop and think about that for a second. Okay, now I know that most of you probably look at this and say, yeah, I know 30 divided by 5 is 6, but we want to get it on that model, all right? So the 30 represents the area, the 5 represents one of the dimensions of the rectangle, and we're looking for the other dimension. Now, we know that the other dimension would be 6 because 6 times 5 would give us the 30, which would be the area of the rectangle. Now, a little bit of vocabulary. I don't use this particular word a lot, but it is a thing that is worth knowing. 30 would be the dividend. That is the number that's being divided. And in polynomial division, we'll, of course, have a polynomial that is being divided. The 5 is the divisor. That's the number doing the dividing. Typically in polynomial division problems, your divisor is a binomial, although if you check out the practice set for this, I do give you a polynomial division where the divisor is a trinomial. It's another huge advantage to using this method for division. And the question mark is the quotient. Of course, that is the answer to a division problem, and that is the word probably that we use the most. Okay, maybe divisor and quotient. Okay. Now, in a division problem, we know the dividend, that is the area. We know the divisor, that's the height, and we are looking for the quotient. That is the base. Okay, I'm going to repeat that because that's what tells us, like, what do we know and what are we trying to find? In a division problem, as opposed to a multiplication problem, we know the area, we know one of the dimensions, that is the height, and the thing we're looking for is the other dimension. So go back to that rectangle with the 30. We knew the area was 30. We knew the height was 5, and we're looking for that other dimension. I can't even count how many times in my own classes on a division problem I have seen students multiply, okay? And that really comes down to knowing what are the things that we're given and what are we looking for. Before we launch into the examples, I do want to take a look at one more thing, and that is, what do we do when there is a remainder? Okay, so we're going to look at the problem 27 divided by 5. So if I do 27 and I do divided by 5, there are actually 3 things that we can do. We know that 5 goes into 27 5 times. 5 times 5 is 25, and I have a remainder of 2. Probably the first thing that you were taught to do in grade school was to simply say remainder 2. Okay, so it's 5 with 2 left over. The second thing that you might do, okay, and just so kind of recap, 5 goes into 27 5 times, and you might do this where you add a 0.0 and you bring that down and you have a decimal point here, and now we say 5 goes into 24 times, and you would keep going like that until either you ran out of places, okay, so like right here we get a remainder of 0, we're done, or to whatever place value your teacher has told you to go to. So if you were asked to go to the hundredths, you'd go out 3 decimal places and then use that 3rd decimal place to round to the nearest hundredth. Now, the one that kind of gets lost, okay, and I'm going to review this because this is what we do in these problems. Same thing, we know 5 goes into 27 5 times, but we do this. We take the remainder and we write it as a fraction over the divisor. And so we would say a mixed number 5 and 2/5, or 5 plus 2/5. And if you were to do a decimal to fraction conversion, 0.4 is actually equal to 2/5. Okay, so you have the decimal and the fraction equivalent of that piece that's left over. This is the one that we use in polynomial division. Okay, so if we have a remainder at the end of our problem, we're going to write a plus sign, sometimes a minus sign. I'm going to leave that up to you guys, whether you want to use a plus sign or a minus sign. Just if you use a plus sign all the time and it's negative, you just got to remember that the fraction is negative, and then over the divisor. Okay. Now, that was like 7.5 minutes of laying the groundwork. The rest of the lesson is just me taking you through some examples. So the first example we're going to look at is that lovely polynomial. So we have 2x to the 4th plus 5x to the 3rd minus 6x squared plus 2x plus 3, and we're dividing that by 2x plus 1. One of the things I love about the area model is that it is no harder to do this problem than it is to do some of what we might think of the more basic problems. The other methods for doing polynomial division, either this is a much more difficult level problem, or the strategy doesn't work for this kind of problem at all. Or you've got to do some gymnastics and bring some fractions into the mix. With the area model, this problem is just as easy to do as any of the others. In fact, it's easy enough that we can start with it as example 1. Now, this is our setup. This right here is our area. Okay, and this right here is the height. So I'm going to set up my rectangle. Now, a good rule of thumb is to look at the degree of the polynomial that you are dividing. Okay, so the polynomial, that's the dividend. And when you set up your rectangle, okay, so here's my rectangle, you want that many columns. So if the degree is 4, you can use 4 columns. Okay, and then my height is going to be 2x plus 1, and so I'm going to need 2 rows. So I know the height, I know the area, and what I'm looking for is this right here. So here's how it works. If you are experienced with multiplication on the area model, you know that the term with the highest degree, or with the highest exponent, is in that upper left-hand corner. And you know that because you've done a ton of them. And so what we do is we're going to write the 2x to the 4th in that upper corner. That is our area, and we're going to start there. Now we can use multiplication. 2x times what would give me 2x to the 4th. Okay, well, the 2 is there. I have an x. I want x to the 4th. Therefore, this must be x to the third. Now you can, one of the other things I love about this method is that you can check it every single step along the way. You don't get muddied in the middle of some like arithmetic. You can check this. So 2x times x to the third, would that give you x to the fourth? Yes. Therefore, you know the x to the third is correct. Now to get this one down here, we're of course going to multiply the base times the height. So we have x to the third times 1, and that is going to give us x to the third. Now remember I said earlier, we're going to leverage the fact that like terms are on the diagonal. So my x to the thirds are going to be right here. So I know that this plus this, okay, because we're looking for the area, x to the third plus this right here, must be equal to 5x to the third, okay, because this one is the area, and here's where the x thirds are. I've got 1x to the third. I need 4 more x to the thirds. And again, I can double check that. X to the third plus 4x to the third does give me 5x to the third. And now I repeat the process. So 2x times what would give me 4x to the third? Well, 2 times 2 would give me the 4, and x times x squared would give me the x to the third. Just kind of double check that. 2x times 2x squared is 4x to the third. Sounds good. To get this one down here, it'll be 2x squared times 1, which is 2x squared. And I keep repeating this process. So now I'm going to continue to leverage the fact that like terms are on the diagonal. So 2x squared plus something has to give me negative 6x squared. Now, if you really, really struggle with that, you can use a number line, okay? A number line would come in really handy. So I've got 0, 1, 2. I'm at the 2. I need to be down here at the negative 6. And so I would go 1, 2, 3, 4, 5, 6, 7, 8 to the left. Therefore, this must be negative 8x squared. And we can do a quick check on that. 2x squared minus 8x squared does give me negative 6x squared. All right, repeating the process again. 2x times what would give me negative 8x squared? Well, 2x or 2 times negative 4 gives me negative 8, and x times x would give me x squared. And now multiplying, negative 4x times 1 would give me negative 4x. And we have to do this again. So we have to leverage the fact that my like terms are going to be right there. And so if I have negative 4x and I want positive 2x, because that's what the area has to be, this would have to be a positive 6x. And there's my positive 6x. And last time, 2x times what would give me 6x? Well, that would be 3. And then 1 times 3 is 3. And before we write down the final answer, let's double check and make sure everything is good to go. If I add up all of these boxes, will I get the area or the dividend? Why, I will, and I know that because of how I filled them in. I have 2x to the fourth, x to the third plus 4x to the third is 5x to the third. 2x squared minus 8x squared is negative 6x squared. Negative 4x plus 6x is 2x, and then the 3. I had the height, and now I have the base. Before you finish the problem, though, make sure that you actually write out the answer, okay? So we want to indicate what the answer is. And so the answer to that division problem is x to the third plus 2x squared minus 4x plus 3. Now that problem took me a little bit less than 7 minutes, and that's with all the explanation and the highlighting and sketching a number line. So it is possible to do these problems much, much, much faster, but even if it's taking you about 7 minutes, 7 or 8 minutes, you should be able to work through the entire practice set in less than an hour, okay? And hopefully it doesn't take you that long, but in case it does. All right, now for this one, I did change the notation a little bit. So remember that you can see these as fractions. And remember our rule of thumb here, we are going to take the degree, and when we set up our rectangle, that's how many columns we want. Okay, and it's not going to be this foolproof thing. On one of the problems, you'll see that like that pattern kind of breaks a little bit, but you won't go wrong with that number of columns. Okay, all right, and then my height is the divisor, so that's 3x plus 2, and here we go. So we're going to take our biggest term, and we know that that has always wound up in the upper left. And so that gives us our starting point. And then we start this like repetitive kind of process of filling in these boxes. So 3x times what gives me 6x to the third? Well, that would have to be 2x squared, and double check it before you move on. So 3x times 2x squared, 3 times 2 is 6, x times x squared is x to the third. Yay. Now right here, okay, we're going to do the base times the height. So 2 times 2 is 4, and then we have the x squared there. So that is 4x squared. On my diagonal right here, okay, so on that diagonal, I have my other x squared term, okay, my other x squared. And together, those need to add up to negative 5x squared. So I know that would have to be, what, negative 9x squared? Okay, negative 9x squared, because negative 9x squared plus 4x squared would give me the negative 5x squared. 3x times what would give me negative 9x squared? Well, that's going to be negative 3x. And again, you can double check it. Say 3 times negative 3 is negative 9. X times x is x squared. And then we'll multiply here by the 2 to get this bottom center one. So negative 3x times 2 is negative 6x. And we've got this going on here. So negative 6x plus this one. All right. Again, leveraging those diagonals right there. Okay. And they together are going to need to add up to 9x. And so that is going to make this a, what, 15x? Yep. And then 3x times what would give me 15x? Well, that's going to be 5. And then 2 times 5 is 10. Now, here's where we have like, this is not right. If I add all of these up, I do not actually get that area. So I've got the 6x to the third, which is fine. I've got the negative 5x squared, and I've got the 9x. But I need a 6, and I've got a 10. This is how you know you have a remainder. If you pictured another box out there, okay, you would ask yourself, what would need to go here in order to get it to add up to 6? And in this case, it's a negative 4, because 10 minus 4 would give you the 6. That number right there is our remainder. So when we go to write the final answer for the problem, we're going to have 2x squared minus 3x plus 5 plus negative 4 over the divisor, which is 3x plus 2. And that was that other little piece of information that I went over with you, which is when you divide, you can write it as the fraction. So you take your remainder and you write it over your divisor. You could also write this, and this is what I meant earlier, I kind of alluded to this. Instead of saying plus negative, you could say minus 4 over 3x plus 2. Either one of those would be correct. Okay, so just either one of those notations would be correct. And that's how we handle the remainder. One more example problem. Okay, now on this one, I want you to notice that there is a missing term here. So I start with x to the fourth, I have x to the third, and then I jump down to x to the first power. There is no x squared. When you're using some of the other strategies for polynomial division, this kind of omission is a really big deal. You've really got to make sure that you set things up correctly or it won't work out. Using this method, though, which you can tell I'm a big fan of this method, you should be okay. It's just going to make the arithmetic a little dicey for us, and I'll take you through an example for that. All right, so because the degree was 4, I'm going to go with 4 columns. And if you ever do too many columns, that's fine. You'll just have columns at the end that you don't use. It doesn't affect like the process at all. All right. All right, so we've got the area set up. We have the divisor, the x plus 3, and we're going to start with that x to the 4th, and we ask ourselves x times what gives me x to the 4th? Well, that is x to the 3rd. And then multiplying to get this bottom left here, we do x to the 3rd times 3, and that gives us 3x to the 3rd. Now here's where it gets weird. I've got a 3x to the 3rd, and I need a 3x to the 3rd, which means my other one right here must be a 0. Okay, and what I like to do is I like to say 0x to the 3rd. Now, technically, 0x to the 3rd is indeed just 0, but I like to preserve the exponents there just to preserve the pattern, okay? Now, here's again where it gets like a little weird. X times what gives me 0x to the 3rd? Well, this is, of course, a 0. All right. Now, you can just write 0, but I'm going to go ahead and write 0x squared. Now, 0x squared is still the same as 0, but here's why I'm doing it. X times x squared would give me the x to the 3rd. Now, I am aware that that's all zeros, but what it does is it preserves the pattern for us. And when we're done, we'll just say, hey, all of those are zeros. So here we have 0x to x squared times 3. Well, we'll say that is 0x squared. Okay, now I've got 0x squared and I want 0x squared. So this is where we just need to be really mindful that that is a 0x squared right there. So 0x squared plus, well, I guess we'd want 0x squared. Okay. And now x times what would give me 0x squared? Well, that again would be 0. This time I'm going to say 0x. Okay, just going to put the 0x there. And 0x times 3 is 0x. And again, what I'm doing is just preserving the pattern. Now, here it's going to kind of go back to normal for us. I have 0x and I need a negative 4x, which means that that right there must be negative 4x. X times what would give me negative 4x? Well, that would be negative 4. And negative 4 times 3 is negative 12. Now, it didn't quite come out right. I've got a negative 12. I need a negative 10. So I can get that with a positive 2. Negative 12 plus 2 is negative 10. So I do have a remainder on that one. And then you have a couple options for how you'd like to write the answer. If you'd like to preserve the zeros in there, okay, and that'll be plus 2 over x plus 3, you can. But there's no reason to write the zeros, so you would be equally correct to just write x to the 3rd minus 4 plus 2 over x plus 3. And again, notice what I did there. By preserving the x's, if you look at the pattern, the exponents, it goes 4, 3, 2, 1. This one goes 3, 2, 1, 0. If you just put the zeros there, you might lose that, and then it makes it a little bit easier to make a mistake when you get down to the end there. But that is up to you. And remember, in the original problem, when you're looking up there, oh, that was a 0x squared. All right, so that's pretty much all that I can really show you. There is at least one practice problem that's going to challenge you a little bit more. A few tips before we leave. Beware of the missing terms and navigating the zeros. They're not impossible. They're just weird, okay? Use a number line to help with your linear arithmetic. So if you're having trouble figuring out what should I be adding here to get to where I want to go, a number line is a visual that can really help. About a year or so ago, I laminated number lines that went from -20 to +20. It might even be -25 to +25 to give my students if they wanted to just have that to mark up so they could count left and right. And the minimum number of columns you need is equal to the degree. So don't have fewer columns than that. It is always okay to have extra columns. You just might not use them. All right, don't forget to like and subscribe if you found this lesson helpful. Check out the practice set for this video. This is definitely one that you need to do to know you understood it. It doesn't matter if this was crystal clear to you, just do the practice, just do them, okay? Drop a comment or question below and check out the other videos and playlists on the channel. I am planning to upload a comparison contrast of the 3 most common methods for doing polynomial division. I'll try to link that depending on what order I post the videos in, or you can check the channel to see if you can find that if you are interested, and I hope to see you in a future video.